The historic Flushing Bridge serves as a centerpiece for the city of Flushing, Michigan. Directly connected to downtown Flushing, this 98-year-old concrete arch bridge is the only Flint River crossing in the city. The rehabilitation of the Flushing Bridge was a compromise solution that both increased the maximum capacity of the bridge and increased its stability. Today, the bridge serves nearly 20,000 vehicles daily. Pedestrians can enjoy this bridge thanks to the Flushing River View Trail that starts at the Flushing Bridge and meanders along the Flint River.
For our analysis of the bridge, we simplified it into a flat beam with supports. This allowed us to use the methods we learned in class to analyze the shear force and bending moment of the bridge under worst-case scenario traffic flow. To remove more complexities in the math, we only analyzed a portion of the bridge between two of the supports. For our analysis, we first found the distributed forces acting on the bridge. Our first force was from the weight of the bridge. To find that, we used the equation W1 equals rho, the density of concrete, times the cross-sectional area, times the length, times gravity. We then solved for the force caused by traffic and the worst-case scenario for the bridge. We used 6 crew cab F-150 work trucks to simulate the most weight the bridge will have to hold based on traffic in the area. The equation used for the force is W2 equals the number of trucks times the mass of a single truck times gravity divided by the length of a bridge section. We then added the forces together to get W total for the bridge. For the W1 equation, rho equals 2,320 kilograms per meter cubed. The cross-sectional area is 1.25 meters times 7.32 meters. The length is 18.59 meters, and gravity is 9.81 meters per second squared. For equation W2, the number of trucks was 6, the mass of a single truck was 2,578.22 kilograms, gravity was 9.81, and the length was 18.59 meters. When using our free body diagrams, our first step toward solving for shear force and bending moment was to find the force AY on the bridge. To solve for that, we used the equation W total divided by 2 times the length of the bridge section. Once we had force AY, we could move to our segment view and solve for the shear force and bending moment. To solve for V, shear force, we used the sum of forces in the y direction and found that V equals AY minus W total times X. For the bending moment, we used the sum of moments around X. We found that M equals AY times X minus W total times X squared divided by 2. We then use these two equations to create graphs of the shear force and bending moment versus distance. The shear force graph fits our expectations very well. Based on the distributed load on the top of the bridge, we would expect the shear force graph to have a downward slope. The load lasts across the whole bridge, and since there is no point forces, the graph will stay continuous and have a negative slope over the whole distance. As for the bending moment graph, we also saw our expected shape. The graph is a parabola that peaks directly in the middle of the bridge. It will have a parabolic shape since the shear force graph was linear. We also know that the forces are symmetrical on both sides of the midpoint, meaning the bending moment graph will also be symmetrical. The graph starts at 0 and ends at 0 as well. During our project, we analyzed the Flushing River Bridge to find the forces that it experiences on a daily basis. Through our research and math, we made various simplifications to the bridge and the forces. While our values may not represent reality perfectly due to these simplifications, we are still able to gain a general understanding of the bridge. This project allowed us to apply our knowledge to a real-world issue and see the applications of what we learned in class this term.